The two previous films were about thermal resistive sensing elements. This film is about one that detects strain, or actually it's a resistance sensor that is a function of position, actually. The position of one end compared to the other. So the X would be the length of the strain gauge, like that. It's sensitive to strain in one direction, basically, and we will look into how it works. Here's a typical image of how it may look if you look through it in a magnifying glass. As I showed in the picture, it has a conductor that runs up and down a patch like this. And then typically added to an elastic surface like this. So what you do is that if you stretch it in that direction, the conductors that are attached to the elastic material will become longer and thinner because of the way it's glued to the substrate. And as you remember, R equals rho times L over A. If we stretch it, the length becomes longer and the area becomes thinner. So the area goes down, the length goes up. And if the numerator goes up and the denominator goes down, the resistance as a whole goes up. So therefore, the resistance goes up when we stretch the strain gauge. It is also possible to compress it. That means that we squeeze it a bit. And if we do that, if we squeeze it, the length goes down, the area goes up, and the resistance as a whole will go down. What if we stretch it in this direction here? Well, that would be more or less like an accordion. The length of the wires will not change very much. So this is the sensitive direction, and this is the non-sensitive direction, I guess. Here. The non-sensitive direction and the sensitive direction. However, it has some sensitivity in this direction as well, but it's neglectable. And it's quite sensitive in this direction here. Going back to the PowerPoint again, we see that we usually connect or glue this strain gauge to a surface. For example, this could be an application for a strain gauge. If we have a wall here, for example, and then we have a bar connected to it, and we attach a strain gauge here. If we now apply a force here, for example, by adding a weight or something, for example like this, like that. Well, if we apply a force to the bar there, the bar of course would bend downwards. So the bar will bend like this, and the strain gauge will stretch, become longer, and thus the resistance will go up. However, there is a specific sensitivity to temperature. And going back to the resistance equals rho L over A. Of course, we have looked at the L and A relationship. That's fine. That has to do with the length and the area. However, there is a row there, and the wire that we have on the strain gauge is usually copper, and you may remember that copper can be used as an RTD. So this row here still has a function of temperature. So therefore, this also has a parasitic temperature dependency. So we have to find some tools to avoid the temperature dependency. What we can do is that we can attach a strain gauge like here and compare the two. Now if the temperature rises, the resistance will go up here and the resistance will go up there as well. But if the force changes, the force here, well, then this one is the only one that will have an increasing resistance. So if we take the result from this one minus the result from this one, the end result depends on the force alone.